In this chapter, we will talk about the fundamental gas laws that describe the behavior of gases under fixed pressure, volume, and temperature conditions. Last time, we described the three states of matter: the solid, liquid, and gas. And we said that solids, they do have definite shape, they do have definite volume. For the liquids, they have an indefinite shape. They take the shape of the container they are in, but they do have a definite volume. This means a 12 mil is a 12 mil, no matter what container it is in. And then finally, gases, they have indefinite shape and they have an indefinite volume because they take the shape of the container and they take the volume of the container as well. So, based on the four physical properties of matter, which are the density, the shape, the compressibility, and the thermal expansion, these are physical properties of matter, we can simply distinguish between the three states of matter. For the shape always depends on the physical state of the matter, if it is a solid, liquid, or gas. Now, the compressibility and the thermal expansion of matter, both they deal with the volume of the matter, whether you apply pressure to the sample to compress or you change the temperature of the sample to expand. And then finally, the density, we define the density to be the mass divided by the volume. In this chapter, we will focus on gas laws. And these are mathematical equations. They describe the behavior of gases as we mix them, as the gases are subjected to different pressure, temperature, or they are allowed to diffuse. The pressure exerted on a gas sample and the temperature of the sample, these are important quantities in gas law calculations. Also, we need to measure the atmospheric pressure. To measure the atmospheric pressure, we use what we call mercury barometers. And a mercury barometer, they use glass tubes. And these glass tubes, they are filled with mercury that sits in a reservoir of mercury. As the air pressure increases, the mercury, so as you increase the air pressure in there, the mercury is going to be forced up the tube. And the tube is marked by measurements to track the atmospheric pressure. So you can go ahead and read the measurement in there to determine what is the atmospheric pressure. There are a lot of units that we use for measuring the pressure. Pressure is the force divided by the unit area. And these are the units. So pressure can be expressed in terms of atmosphere, in terms of millimeter Hg, which is mercury, in terms of torr, in terms of bar, and Pascal. So no matter what unit you use, you can use these conversions here, and you don't have to memorize. Just write them on a piece of paper and use them whenever you're converting from one unit to the other. There are multiple gas laws, and these gas laws, they are named after the scientists who first discovered them. The first law is the Boyle's law, and Boyle's law states that as the pressure increases, as the volume is going to decrease at constant number of moles and temperature. So the volume is inversely proportional to the pressure. So let's say, for example, if you have a container, you have a gas in the container, and then you are applying a pressure to the gas. So if you are increasing the pressure that you're applying in there, you're going to compress the gas, right? So if you're going to compress the gas, the volume of the gas is going to decrease. So we end up having a relationship between the volume and the pressure. So PV, this is equal to constant, because you're doing it at a constant number of moles and constant temperature. So this will result with our first equation in this chapter, which is the Boyle's law equation. This is P1 V1. This is the initial pressure and volume of the gas. and this is the final pressure and volume of the gas after the compression. Guys, if you take the volume and you plot it versus the pressure, PV, you're going to end up getting a hyperbola. Versus if you take the volume and you plot it versus 1 over P, so 1 over P is going to be in the x-axis, the volume in liters. Always the volume in these types of problems, it should be in liters. So if you're given the volume in any unit, you have to change the volume into liters. So the plot of the volume versus 1 over P is a straight line. And this is more useful information because it results in an equation of a straight line, and the slope of the equation is m. Let's have an example. So an 8-liter sample of the nitrogen. So remember, Boyle's law happens under constant temperature. So if I want to use this equation in the given, I need an indication that I am using the conditions under a constant temperature. So the temperature should not change, okay? Or they should not mention the temperature in there. So see, they are saying over here at a constant temperature. So they are not changing the temperature. So I know exactly that I'm going to be using the Boyle's law. Normally in these types of problems, you go ahead and you state the given. So write the given. And what you have over here is our first volume, which is V1, that is 8.00 liters. And again, volume is always in liters, and if it is not in liters, please change it into liters. So you're given the sample of nitrogen. Nitrogen is a gas, okay? So it has an 8-liter volume at a pressure of 500 torr. So my pressure, which is P1, is going to be 500 torr. This is the initial volume and the pressure in there. Now at a constant temperature. Okay, so now they're going to change. So what must be the pressure to change the volume? So now I have V2 is equal to 3.00 liters, and you can easily see that you are compressing. You're going from volume A to volume 3, so you are decreasing the volume, so you're compressing the sample, and what they need is the pressure in there. So they need P2. Okay, so we're going to go ahead and write the formula down. P1 V1 is equal to P2 V2. And normally this is what I do. What you need is P2, right? So you are going to divide by V2 here. You're going to divide by V2 there, so that you can end up getting an equation of P2. So now P2 is equal to P1 V1 over V2. And that is equal to 500 torrs. Sometimes the pressures that are given, or sometimes they will specify for you the unit of the pressure that you are going to calculate. But here we are not specifying, so we're going to keep it in torr. No need to change it. So this is 500 torrs times 8.00 liters divided by 3.00 liters. Notice the volumes are the same unit, so I can cancel those out, and my answer is 1.33 times 10 to the 3 torrs. So the second law is Charle's law, and Charle's law deals with constant pressure this time, not temperature, it's a constant pressure. So it's a constant number of moles and constant pressure. So now what we are changing is the volume and the temperature, and these are proportional to each other, not inversely proportional. Notice up there, they were inversely proportional. So as you increase the volume, you decrease the pressure. Here, no, as you increase the volume, you increase, or as you increase the temperature, you increase the volume. So let's say, for example, if I have a container with a sample of gas, I heat the sample of gas. So you know, when you heat the sample of gas, what's going to happen in there? The volume is going to expand, right? So the volume is going to expand in this case at a constant pressure. So the pressure is a constant in here. I'm not applying an external pressure there. The pressure is going to be constant. So as I am heating the sample, the the sample is going to expand. So it's going to increase, as simple as that. So as the temperature increases, as the volume is going to increase. So I would say, okay, V over T is equal to K, which is constant. This means that this is the second equation. V1 over T1 is equal to V2 over T2. Whether you plot the graph using the Celsius or the Kelvin, we prefer the Kelvin because it will pass by the zero intercept. But you can plot it using the degrees Celsius, no big deal in this case. But V1 T1 is equal to V2 T2, and it is a straight line. So let's have an example. A 255 ml sample of nitrogen gas at 75 degrees. So you can see here they mentioned the temperature, and they are changing the temperature. This is your temperature initial, this is your temperature final. You're heating the sample, so you're expanding it. So the volume is going to increase. So I know over here that I started with that much volume, so my final volume needs to be more, okay? So in these types of problems, you guys just remember, and it's a very important note, that the temperature, it has to be in Kelvin, okay? So the temperature has to be in Kelvin. It should be in Kelvin. This means that I need to change the temperature from Celsius to Kelvin for each one of them. This is in all gas law equations. Okay, so this means that I'm going to change degrees Celsius to Kelvin. And by definition, degrees Celsius, this is equal to, actually, let's put it this way. Degrees Celsius plus 273, this is going to be Kelvin. So you're gonna simply add 273 to the Kelvin. So that is going to make both temperatures. This is 75 plus 273. This is a 348 Kelvin. And the second one, it's 250 degrees Celsius plus 273, and this is 523 Kelvin. So let's lay down the given. You are given V1, which is 255 milliliters, and you are going to find V2. You are given the temperature T1, which is 75 degrees Celsius, and T2, which is actually, instead of writing it in Celsius, we're going to write it in Kelvin. This is 348 K, and this is 523 K. Okay? We know that the formula for the Charles law is V1 over T1. That is equal to V2 over T2, right? So what we need over here is V2, so we can go ahead and arrange the equation. And what I would like to do, this is V1 over T1. So what I would like to do is first to cross multiply. So I would say, okay, so to arrange, I would have V1 T2 is equal to V2 T1, right? And then I need simply V2. So if I need V2, I will divide by T1 here and divide by T1 there. T1 and T1 cancel out, and this is going to be my equation. So my equation is V2 is equal to V1 T2 over T1. And then I go ahead and do the substitution, which is 255 milliliters. Okay, so very important note, volume. So volume here, I'm going to keep it in mils. I don't have another volume. So the point here is I need the volumes to be the same unit, and preferably in liters. But when I have one volume and I want to find the other, I don't need to change this unit into liters unless I am asked to express the volume at a certain unit in there. But here I can leave it in mils. What I care about is the temperatures to be in Kelvin, both of them. This is what I care about. So that is times 523K divided by 348K. K and K cancel out, and then you're going to end up having 383 mils. Notice over here that the volume expanded, right? This is our initial, this is our final volume. So expanded as the temperature increased. The volume expanded in this case, which makes sense. Always your answer has to make sense. In the example before, the units, they do have to cancel out for the volume. So whether the units are in both liters or whether they are in mil, they have to cancel out. I personally prefer the units to be in liters every single time because once we start with ideal gases, the volume has to be in liters. It cannot be in milliliters.